Hello. So in this video, we are going to be talking about whole discontinuity, H-O-L-E, not no W. So whole discontinuities in a function. So wholes, in general, these things tend to happen when you have a domain restriction that can then be removed by simplifying. There are some other circumstances where they can happen, but we're not going to run into that in this because we need calculus to identify those. So in those situations where you can remove the sort of problem, the domain restriction as a process of simplifying, that will give you a whole discontinuity. So let's look at an example. So let's say we have r of x here. We have the x plus 1, x minus 2, x plus 3 squared, etc. So again, we want to, before we do any simplifying, record the domain, because the domain depends on the initial function, not the simplified function. So the domain here, we don't want the -1, -2, or -3 because that's when the bottom would be 0. Dividing by 0 would be bad, right? The top and bottom functions individually, they're both polynomials, so there's no other restrictions you have to worry about. It's just that dividing by 0 bit. Okay, so after we simplify it, though, we get down, so we can cancel out the x plus 1 on the top and bottom and one of the x plus 3s on the top and bottom. We get down to this x minus 2, x plus 3, and x plus 2 in the bottom. So the x plus 2 in the bottom, that's going to cause a vertical asymptote. There's a different video on that if you haven't seen it yet. So if you haven't seen that yet, magic, but there's a way of telling that happened. But what about the other domain restrictions, right? So here, there was the x minus 2 domain restriction that sort of survived the culling process, but the x minus 1 and x minus 3, those vanished, right? So what we want to do with those is plug those into the simplified version and see what we get. So if we plug in -1, well, then we get, -1 minus 2 is -3, -1 plus 3 is 2, -1 plus 2, 1. That gets us -6, right? Likewise, if we plug in -3, we get -5 times 0 over -1. That's just 0. Now, the important part is that when we plugged in these values, they worked. They gave us numbers. There was no dividing by 0. There was no crazy, it went off to infinity or some craziness, right? It just sort of gave us a nice, finite, concrete number. That's how you know that they're a whole discontinuity, right? So we know now that there's a whole discontinuity at -1 and -3. But these holes are holes in the graph, meaning that they're sort of points on the graph that are missing. So it's often sort of useful to talk about them as the points that you wish were there, meaning that you want an x and a y value, the coordinate pair. And the nice thing is that by plugging it in and checking, that gave you the y values, meaning that when we plugged in -1 and we got -6, that is the location of the hole. So we have a hole at -1, -6, right? Likewise, when we plugged in -3 and got 0, that means there's a hole at -3, 0. And if we were to graph this thing, we would see, a curve that went through -1, -6, and through -3 and 0, but those points themselves would be missing. They'd be little, open circles on those individual points because of the domain restriction up here, okay? So what do? Well, we talked about whole discontinuities, and in particular, how to find them sort of analytically-ish, right? Because it takes calculus. We don't have calculus, but there is sort of a nice way of doing it under these particular circumstances where whenever you have a ratio, a rational function, and you can remove some of those domain restrictions as a course of, over the course of simplifying, being able to remove them means that they're whole discontinuities. And then when you plug them back in and get a nice concrete finite number, nothing crazy happening, that tells you that they were indeed whole discontinuities, but it also gives you the y value of the whole. So you have an actual point that represents the whole discontinuity. Okay, so that is that.